Hi guys, welcome to your first video in Chapter 8. We are going to introduce something that you've probably seen coming since Chapter 7, and that is the linear model, or the best fit line, or the least squares regression line for data in a scatter plot. Now, on this first slide, we're going to recap with something that hopefully virtually all of you guys are good with, but I found 2 years ago when I first taught this class that I was midway through working with the regression line, and I had a couple of kids who did not remember slope-intercept formula for a line. So we're going to start with a quick recap there. Recall that y equals mx plus b is the generalized form of a linear equation written in slope-intercept, where that linear equation has two parameters, two things that make it different from line to line. The first is m, which is your slope, okay? And m, being your slope, represents the change in y, your y variable, divided through by the change in your x variable, which I don't know that the book will represent it this way, but sometimes you'll see that change in y over change in x represent or abbreviated as delta y over delta x, where delta means change in. If you've got a line already on a graph and you pick out a couple of points on that graph, let me see if I can pick out a few here that work okay. Let's go with this guy as well. So between these 2 points, my change from the lower to the upper is 3 units in x, and my change vertically, my change in y, is, let's see, that is 1.5. So my slope here, m, would be equal to 1.5 over 3, which reduces down to just 0.5 or 1/2. Okay, so there's slope given 2 points on the line. Now, the second piece, the second parameter, there's your first parameter. B, from the y equals mx plus b, that is your y-intercept. That is where our line hits the y-axis. And it does so, obviously, look at the coordinate plane, it does so wherever x is equal to 0. So b is really, if I'm disregarding that mx because our x value is equal to 0, b is really just the y value where we're hitting the y-axis. That has a lot of meaning in statistics, especially with scatter plots. Our variables are coming from the real world. So if you've got, let's say on your x-axis you were tracking height, and on your horizontal, or excuse me, your vertical axis, your y-axis, you were tracking weight, that would, if you are looking at a y-intercept, that would be, okay, what does my line that best fits through the data predict someone's height would be if they weigh nothing? That is, what is my model saying someone's going to weigh, even if they don't exist, even if there is no person? That's maybe a silly example, but something I came up with off the top of my head. Y-intercept is important for virtually every scatter plot you're going to work with. All right, so building the linear regression model. In this next slide, you've got a scatter plot that I showed you in Chapter 7 Part 2 notes already. The data is not characterized by height and weight, or shoe size and GPA, whatever those two variables might be, but instead we've characterized the data by standard deviations from the mean of x and standard deviations from the mean of y. This is the building block upon which we can build a general linear regression line, an equation to come through all of the scatter plots that we're going to encounter. It's all based upon this standardized scatter plot. Standardized basically, again, meaning data characterized by number of z-scores. Okay, so our line, let me go to black for this. Our line that we're building here runs through this very important point right here. And that very important point is where the z-scores in x are equal to 0 and the z-scores in y are equal to 0. And we know that the z-scores are the standard deviations from the mean, so this has the same meaning as x bar, y bar. That is to say, the line that we're going to come up with runs through the very center of the data, the mean of your x and the mean of your y. That's important. It's one of the things that we need to know to be able to build a regression line, a best fit line for every new scatter plot that we encounter. Okay, so our line goes through that point, and it may, for instance, look something like this right here, our best fit line. I don't really care, and I don't think that the AP exam cares either if you do this at the end of your line. That's just pure nitpicking. We don't really care with the scatter plot to say what does this line predict if the line continues forever. That in the real world context, looking at negative infinity and positive infinity doesn't have a whole lot of meaning. So those guys don't have to be there whenever you draw a line through a scatter plot to represent your best fit line. But one of the things about this best fit line that's important to note is that we're not necessarily hitting the points. Sometimes we may hit the point there in the upper right, but in general, this best fit line is going to miss the vast majority of them, and that's okay. This line is not telling you what your actual y values are. It's doing the following. Let me get the red here real quick. For any point on this regression line, we have, like this guy right here, that is some number of standard deviations from the mean of x, followed by, vertically, we're looking at the predicted value, the predicted number of standard deviations from y. The best fit line is a predictor. It does not try to hit all of the data. Okay? So all of these points in, let's not do blue, let's do green, so we're not thinking in terms of how correlation is built. All of these points here, all of them would be some number of standard deviations from the mean of x, some number of standard deviations from the mean of y, versus any point on your regression line is some number of standard deviations from the mean of x. Yes, right here, but we're predicting what the y value is going to be for this from this line. Okay, let me take away the green. That's not really essential to us building the regression model here. Okay, so we've done two things. We've talked about what these points will look like on the regression line. We've talked about the fact that we're running through the very center of the data, x bar, y bar. So we are trying to build the following. We want sum y equals mx plus b. We want the equation and slope-intercept form of this black line that we've drawn through this scatter plot. Well, we know the following. We know we're not working with y and x. We already talked about the fact that all of this data in this scatter plot was standardized. Basically, you'd plugged all the numbers for x, all the numbers for y, into your z-score equation, so you found the standard deviation from mean of both x and y. So we can update the y equals mx plus b to be the following. It's really number of standard deviations from the mean of y that we're predicting. This hat, which I don't think I really mentioned that up here, the hat is referring to a predicted value. We're predicting what the y value is going to be in this line. Equals to our slope of m. X is actually standard deviations from the mean of x, plus your b value, your y-intercept. Okay, well, there's a start. We've updated just a little bit. We can update this a little bit further based upon the fact that we know we run through 0, 0. When the z-score is equal to 0 for x, the z-score is equal to 0 for y as well. So what does that mean? Well, if you're trying to find your y-intercept and you plug in 0 right here, that middle term directly to the right of the equal sign falls out entirely, and you would just get 0 equals b. So we have the following. The predicted z-scores in y are equal to the slope of our black line times the number of standard deviations from the mean in x. And b is fallen out because it would just be 0. And last little bit here, and this is where I'm going to wave the hands, and given that the next time I see you guys I will be passing out books, I'm going to direct you to, if you're curious about this, you're welcome to look at a math box in chapter 8 that explains this further, but I don't think it's worth illustrating here. The slope of our black line, you probably aren't going to be too surprised to find out, is actually R, the correlation coefficient. Some of you guys, when we took our first chapter 7 video quiz, wanted to say, instead of, oh, actually that's not pertinent. That's not pertinent. Regardless, R is equal to M. The correlation coefficient is the slope of your regression line. So this is as updated as we can get. Z hat sub y, the number of standard deviations we predict to be from the mean of y, is equal to the correlation coefficient times our standard deviations from x. Okay, that is the regression line. That is the best fit line through our data if the data is standardized like this. If you're not working with typical variables of feet, height, inches, GPA, shoe size, weight, etc., etc. If you're strictly talking in terms of standard deviations, what we've got in black is how you could make sense of this regression line. All right, so we said from here to here that our slope is just equal to the correlation coefficient. I want to highlight something there, and to do that, let me scroll down here. So if our slope is equal to R, and going back to Algebra 1 class, I'm sure that you worked with slope as a fraction, so let's represent it as a fraction here as well. If the slope is equal to R over 1, then that means, given what our variables are, standard deviations from mean of x and standard deviations from mean of y, that for every one standard deviation increase in x, we are changing our standard deviations in y. Okay? Again, that's just based upon the fact that we've characterized our data by z-scores. So everything's built off this standard deviation. So our slope predicts that for every, if I go out one standard deviation from the mean of x here, let me pull that up to this point, we should have gone up our standard deviations in y. That's what the slope means, if the correlation coefficient is our slope for this thing. Okay, let's go on to the next slide. We're going to use this tool that I boxed in black. That's our building block, as I mentioned before. All of the last slide aside, it's obviously not helpful to have an equation which describes the best fit line through our data only under the conditions that our data is being expressed in terms of z-scores from the mean and the mean of x and the mean of y. We want to tweak this equation just a tad to be more suitable to all sorts of scatter plots. So we want the following. We want to take this guy that we just developed, this predicted change in z-scores for y equal to the mean, or not the mean, the slope of the correlation coefficient times z sub x, the standard deviations from the mean of x, and we want to make it look something like the following. We want to see a y hat where y is any response variable that we've got equals to some slope times x, where x is any explanatory variable we've got, plus b, our y-intercept. Okay, so how do we do this? Well, the first thing to note, we said just last slide that the slope for a standardized scatter plot, where everything's in terms of standard deviations, was equal to r over 1 expressed as a fraction. So that meant r standard, oh, I want to look at the denominator again. That was for every 1 standard deviation increase in x, we are changing r standard deviations in increase and y. Okay, so let's ask ourselves the following. If I'm not just talking strictly in terms of standard deviations, but now I've got units, what is one standard deviation in increase in x? Well, that's just the standard deviation of your x variable. So that would be s, and I'll put a subscript here of x. Whatever the standard deviation is that you could get from your calculator using 1-bar stats, the standard deviation for your explanatory variable, that is a single standard standard deviation increase in x. Okay? So secondly, what is our standard deviation increases or increase in y? Well, that would just be r times s of y. R times what the standard deviation is for y. So, what does all of this mean in terms of trying to go from here to here? We can say the following. We can say that our slope has got to be, for a general scatter plot, r's hanging around times sy, because we just said that it was equivalent for our standard deviation. Our standard deviation increases in y was just rsy, and a single standard deviation increase in x is just s of x. There's our slope. So we've got the first of the two parameters that we need. Okay? Secondly, how do we get the b value? Well, remember last slide we talked about the fact that our best fit line is going to go through the very center of the data. We mentioned that the best fit line will run through the mean of x and the mean of y. So we can update this as follows. We can say, well, to get b, we're going to take the generalized slope-intercept form of the line and plug in the mean of y and the mean of x. So we know our regression line will go through this point with a slope of what we just said it would be, r sy over sx times the mean of x, x bar, plus b, and b is what we're trying to find right here. So when we solve this equation for b, for the y-intercept, we get the following. Our y-intercept has got to be the mean of y minus our slope r times the standard deviation of y over the standard deviation of x, multiplied by the mean of x. Okay? So there you go. We have found all that we need now to be able to build a linear model through any scatter plot. Okay, before we go on here, notes about this linear model. Two things here. Our linear model, oh, I did put that. Okay, y hat. Our linear model y hat equals mx plus b has two parameters. The first is m, represented by your, or which is your slope rather, and the second b, your y-intercept. To find the slope, notice what we did here. That was this circle in black right here. We needed three things. Slope depends upon you knowing your correlation coefficient through the scatter plot, which you can find on your calculator now. I've shown you how to do that. You do not need to calculate that by hand. You're looking back at this, your standard deviation for x and the standard deviation for y. How do you get both of those things? Well, if you've got two lists set up for your y variable and your x variable, you can use 1-bar stats twice. You can say 1-bar stats for your y variable. That'll give you the standard deviation for y. 1-bar stats for the x variable. That'll give you the standard deviation for x. Similarly, to find your y-intercept, you need all those things we had just mentioned to get your slope, but you also need the mean of y and the mean of x. Again, for your y-intercept, to get the mean of y and the mean of x, you're again just using bar stats. That comes from the same source. Okay, so we've been through kind of a long derivation of how you can get everything that you would need to come up with that first circled equation. It's going to be a best fit line for any scatter plot. There are three conditions that you have to make sure are met to be able to build a linear model for your scatter plot. The first condition that's got to be met is called the quantitative variables condition. Now, this you would think would be a no-brainer, but the book does a pretty good job of sending you problems that will trip you up from time to time. If you've got variables, for instance, of eye color, which may be coded according to 1, 2, 3, 4, maybe 1 is equal to blue, 2 is equal to green, etc. And you've got weight on your vertical axis, obviously maybe in pounds, whatever. Don't be fooled by the fact that you've got nothing but numbers on this coordinate plane. You've obviously got eye color masking as a quantitative variable when it's a qualitative feature, okay? So this guy's got to be met, the quantitative variables condition. Second thing that's got to be met, we're building linear models. So you've got to make sure that you've got a fairly good linear form in your scatter plot. For instance, and this too I feel like is normally a no-brainer, but it bears mentioning. If I'm seeing a quadratic form between x and y variables, this would not be an appropriate time to use a linear model. So pay attention to the form of the data before you build a linear model. So there's the second piece, straight enough condition. And then the last piece, the outlier condition, all based upon the fact that the linear model that we just built for a scatter plot that we will apply next slide depends upon, let me put down some sample data here. Okay, it depends upon the correlation coefficient. And the correlation coefficient, that first red circle, red and black both, determines your slope. We know from what we mentioned in Chapter 7 that your correlation coefficient is built from looking at all these standard deviation boxes, which are the difference from the mean of your y variable and the difference from the mean of your x variable. If you've got an outlier like this guy over here, it's going to make your slope look really weird. Your correlation coefficient is going to be thrown off from the fact that you've got a negative z-score here for x, positive z-score here. Correlation coefficient multiplies the two, so you've got a huge negative effect from that one red point. Your slope is therefore going to look more negative as a result when you've got an otherwise very strong linear positive trend in the data. So how do we fix that? Well, just as I had mentioned that you would do with a histogram, if you've got an outlier that's throwing your data off, you should really show the linear model with the outlier in the data, and then you're going to calculate the linear model one more time, having removed the outlier. And again, just as a quick recap, pay attention to when you've got data values that A, are not following the trend of the rest of the data, but they're also very far from the mean of x and the mean of y. Those are the two things that you're looking for that will determine whether or not you've got an outlier in your scatter plot. Okay, so there are the three conditions. In this chapter, I don't think you're going to encounter a lot of problems that don't meet those conditions. There will be a few, but when we hit chapter 10, we're going to look at how we can use our linear tool in applications that are not naturally linear. We're going to fix data so that it'll become linear. We're going to re-express data in chapter 10. So we're going to talk more about the straight enough condition and the outlier condition in chapters to come. The quantitative variables condition is important to pay attention to from the get-go. All right, let's look at a practice problem together, and then we will be done with the notes. I need to check the time real quick. 24. Okay, so this is going to be a little bit longer, but we shouldn't go past 40. The SAT is a test often used as part of an application to college. SAT scores are between 200 and 800, but have no units. Before 2005, tests were given in math and verbal areas. That's the SAT I took as well. Doing the SAT math problems also involved the ability to read and understand the questions, but could a person's verbal score be used to predict the math score? Verbal and math SAT scores of a high school graduating class are displayed in the scatter plot with the regression line added. Describe the relationship. Well, you've got, anytime you're doing a description of a scatter plot, you're relying on strength, direction, and form. Strength here I would characterize as somewhere between moderate and weak. We don't have a very tight clustering of the data. The form is approximately linear. I mean, it is, the math scores are increasing as the verbal scores increasing. And we're not seeing any curvature in that form. So I would say it's approximately linear. And then the direction, obviously positive, because as I just said, as verbal increases, so too does the math. So your slope, well, not your slope, but the direction is positive. B here, are there any students whose scores do not seem to fit the overall pattern? So this is a question of, do we have outliers? Yeah, the way that you're looking for outliers here, you're looking at where's the mean of my x variable versus where's the mean of my y variable. What points are far from that center, so to speak? Okay, well, you've got this guy right here that looks like a clear outlier. He's got a verbal score of maybe 504, 510, and he aced the math section. So go him or go her. You've got another outlier over here where you've got almost the opposite happening. You've got a very low verbal score. Maybe this is a student who's new to the States, and they're still taking the SAT to try to get into college. Who knows? Regardless, very low verbal score. Math scores that's are actually above average. 500 is where they try to build the average for both math and verbal, and then they try to make the standard deviation on all the SATs 100. Okay, so yeah, we do have those two. We've mentioned them. C for these data, R equals 0.685. Interpret this statistic. Well, I can tell you right now, anytime on the AP exam or in the textbook they're asking for you to interpret R, they are looking for almost exactly the following. And this is all based upon the fact that if you consider the data of a scatter plot in terms of z-scores, we said that the slope of the regression line, if you're looking strictly at z-scores, was just R. And that R meant for that every one standard deviation increase in x, we would see R standard deviation increases in y. So we're going to use exactly that tool right here, and we're going to say that R equaling 0.685 means, and if this helps you out, put this over 1, that for every one standard deviation increase in x, in this case, is the verbal score, and a student's verbal score, the linear model predicts a 0.685 standard deviation increase in your y variable here, which is your math score. Increase in a student's math score. Okay, now let me do one thing on this scatter plot that may have been helpful before this point. But, so what? I'll go ahead and do it now. Any of these points on this regression line are going to be some verbal score and a predicted math value. It is not necessarily a particular student's math value. It's just what the line is predicting for us. So notice that every time I've been checking out these points on the line, we're using the explanatory variable to predict the response variable here, which makes sense. That's why we took so much time and spent so much, paid so much attention to explanatory response, because in this case with the linear model, you're using x variable to predict y variable. All right, we've got the conclusion of this problem that we're still looking at. They say indeed these verbal scores average 596.3 with a standard deviation of 99.5, and the math scores average 612.2 with the standard deviation of 96.1. They want the equation of the regression line. Well, the verbal scores are our x variable here. We can say that you can represent this a couple of ways. If you want to talk about your regression line being y hat equals mx plus b, then the verbal score average of 596.3 would be your x bar. Or if you want to characterize this regression line or write this regression line instead as math hat, the predicted math scores equals m times your x variable here is verbal scores plus your y-intercept. Then 596.3 would be the mean, that's VIN, not verbal. The mean of your verbal scores, verbal bar. Okay, verbal bar is 596.3, standard deviation of 99.5. So the standard deviation with respect to verbal is 99.5. The math scores average 612.2, so that would be math hat, or bar rather. The mean of the math values, standard deviation of 96.1 would be your standard deviation with respect to math. We want the equation, the regression line. Well, a couple slides ago, 3 I think, we talked about how, let me find my place here real quick. If our regression line we're going to write as the predicted math score equals the slope times our verbal score, which is our explanatory variable, plus our y-intercept, to get m, that would be equal to our correlation coefficient, which they actually gave us last slide, that 0.685, times the standard deviation in y, where y is math. So that's going to be 96.1, standard deviation in math, over the standard deviation in our x variable, which in this case is verbal, s sub verbal. Okay, so this is a plug and chug. Let's find the slope by saying, okay, I think it was 0.685 times standard deviation for math is 96.1, divide through by your 99.5, and you get the following, which is awfully close to the correlation coefficient. The correlation coefficient at 0.685, we obviously multiplied, then divided by two numbers that were awfully close to 100. So we didn't get a huge change in our slope from the correlation coefficient of 0.685. All right, so that's our first parameter for our model. We still need the y-intercept. The y-intercept we said would be b equals your, because the data runs through the mean of both variables, it's the mean math score minus our slope times the mean verbal score in this case. I have solved that first red line for b and plugged in the mean for both math and verbal into the math hat and verbal variables here. So b would be equal to the mean for the math scores we said was 612.2 minus our slope we just found times the mean of our verbal scores, 596.3. That y-intercept comes out to be 217.4. Okay, so they wanted the linear model. The linear model, all said and done, would be math hat, our predicted math value is equal to a slope of 0.662 times whatever verbal score you plug in, plus your 217.4. Okay, let's talk real quick about what this guy means. Some of you guys I'm sure know this very well, some do not. Again, y-intercept, where are we hitting the vertical axis? So this would be, although the scatter plot doesn't do a great job of showing this, if you plugged in a verbal score equal to 0 right here, we would predict that you would still get a math score of 217.4. So if you absolutely flunked the verbal section, the model would predict a 217.4 for math. All right, so there is D. Interpret the slope of this line. The 0.662, which I've already circled, well, that would mean that if this helps you, put that number over 1. For every 1 increase in verbal, remember slope is change in y over change in x, so change in math over change in verbal. For every 1 increase in your verbal score, you would expect to go up 0.662 points according to the model in your math score. The model would predict a 0.662 increase in your math score for every 1 point increase in your verbal score. And then last little bit here, what's F asking for? Predict the math score of a student with a verbal score of 500. Well, now that we've got our model right here, in F, all we're going to do is say, well, if they want to know what the model predicts for a particular math score, we know our slope now. They just told us what the student had scored in the verbal section of 500, and we know our y-intercept. That's just a simple matter of plug and chug. So the predicted math score for a particular student with a verbal score of 500 should come out to be 548.4.